Okay, so we have question 6. It says a student investigated the reaction rate between magnesium and sulfuric acid. The balanced equation for the reaction rate that takes place is as follows here, as we can see. Then it says the student repeats the experiment a few times with different concentrations of sulfuric acid. All the other variables are kept constant. Then as we can see here, the results are recorded in the table below. We have different concentrations of sulfuric acid and also with different reaction rates measured in centimeter cube per second. And then 6.1 says formulate an investigative question for this investigation. So for that one, 6.1, the investigation question goes as, remember with investigative question you want to have what is, right? So they say what is the relationship between the concentration of the sulfuric acid and the reaction rate. And then 6.2, write down one variable that must be kept constant. So what must be kept constant here to ensure that the results we obtain are valid and reliable? We obviously have to maintain the same amount of magnesium, since the relationship that we are looking at here is between the concentration of the sulfuric acid and the rate of reaction as guided by our investigative question. So we would need to keep the mass of magnesium constant, and also we will need to keep the temperature constant. Remember, if we don't maintain the same temperature, that means we are not truly sure if the results are as a result of the different temperatures that we exposed the particles to, or whether it is truly the concentration of the sulfuric acid. So it is very important that we maintain our temperature constant in all these experiments, or in all these parts of the investigation, so that we know for sure that the concentration of the sulfuric acid is the one and the only factor that is affecting the affecting the rate of the reaction rather. Then 6.3 says, what will be the effect on the reaction rate if lumps of magnesium are used instead of powdered magnesium? So write only increase, decrease, or remain the same. So instead of using the powdered magnesium, they choose to use lumps, right? So we know with lumps, we have a smaller surface area here with lumps, and with powdered magnesium we have a larger surface area. So with a larger surface area there is a higher reaction rate, and with a smaller surface area there is a lower reaction rate. Then they say write only increase, decrease, or remain the same. So we know the reaction rate if they use lumps instead of powdered magnesium will decrease. So 6.3 we say decreases. Then 6.4 says use the collision theory to explain the answer to question 6.3. So we want to explain the answer to question 6.3 for 3 marks. We want to give a reason why lumps will produce a lower reaction rate other than using the powdered magnesium. So we'll say the lumps have a smaller surface area, number one, therefore less particles will be exposed. So with a smaller surface area, less particles are exposed, then there will be less collisions with correct orientation. So this limits our collisions with the correct orientation. And if there is less collisions with correct orientation, that means there will be fewer effective collisions per unit time, and thus the reaction rate will decrease. Right, so that's how we explain this according to the collision theory. So we say smaller surface area, therefore less particles will be exposed, there will be less collisions with correct orientation, and therefore fewer effective collisions per unit time, and thus the reaction rate will decrease. Okay, then 6.5 says what will be the effect on the rate of reaction if the temperature increases from 20 degrees Celsius to 30 degrees Celsius, right? Only increase, decrease, or remain the same. So we know an increase on temperature has a positive effect on the rate of reaction. So that means our answer for 6.4 is obviously increase. It says an experiment was conducted to investigate the rate of reaction between excess calcium carbonate and dilute nitric acid. The balanced chemical equation for the reaction is given below. As we can see here, this is a balanced equation. And then in flask A, we are given 200 centimeter cube and 0.3 mole dm cube of nitric acid at 25 degrees Celsius room temperature. And then in both flask A and flask B, we are given 4.5 gram of lump of calcium carbonate. And then flask B, we are given 300 centimeter cube, 0.3 mole dm cube of nitric acid at 25 degrees Celsius. Then 6.6 says calculate the volume of carbon dioxide produced at STP. Now you can see we are given at STP. That means in this one we are allowed to use our molar gas volume as 22.4 dm cube. So remember, once they say STP, that means our molar gas volume will be 22.4 dm cube, unless of course stated otherwise, but then this is always our constant. Then now let's check. They say calculate the volume of carbon dioxide produced at STP, but here we are given the information of nitric acid. Now, knowing our stoichiometric calculations, we know that we have to calculate the number of moles of the nitric acid and use our ratios to compare the number of moles of the two. So we'll use the ratios to get the number of moles of the carbon dioxide. So this is 2:1. We can figure out the ratio here is 2:1, and then now we know we have to find the number of moles of the nitric acid. But what formula are we going to use? We can see here that we are given the volume. So our formula, our choice of formula will always be guided by the data that we have. We have the volume here, we have the concentration. We know the formula that we can use for this one, if we have that data and we are looking for the number of moles, is the one for concentration. Concentration is equals to number of moles over the volume. So now we are looking for the number of moles, but then we can see that we have a problem with the volume here. It is given in centimeter cube, but we always want it in decimeter cube. So what are we supposed to do? We will take this 200 centimeter cube and divide it by 1,000. So this is how we convert centimeter cube to decimeter cube, by dividing by 1,000, and then we'll obviously have 0.2 dm cube. So now we have all that. We can now calculate the number of moles. So its concentration is equals to N over V, and then what is our concentration? We are given 0.3. So let's note that we are calculating here for the nitric acid, and then it's equals to number of moles over the volume. The volume we are given as 0.2, and then obviously we'll just cross multiply here. This is 0.06 mole. But then remember, we just found the number of moles of the nitric acid, but then what we are actually looking for is the number of moles of the carbon dioxide. So we'll say the ratio of nitric acid to the ratio of carbon dioxide is 2:1. So we have our number of moles as 0.06, meaning here we'll have X, and then to calculate this, to calculate the number of moles of carbon dioxide, we understand that the number of moles have to be half that of the nitric acid because of the ratio 2:1. So 2 parts of this only need 1 part of that, and then 0.03 mole. Now, to calculate then the volume of the carbon dioxide, we have the number of moles. So we say the number of moles of carbon dioxide is 0.03 mole, and then since they said at STP the carbon dioxide is produced at STP, and we know the formula for STP is N is equals to V over Vm, so we already have the number of moles, it's 0.03, and then here we have our volume, which is the one we are looking for, the volume of carbon dioxide, and then the Vm, remember this is our molar gas volume at STP, which is 22.4, and then we just cross multiply here, our volume will be 0.672 dm cube, and then that's how we have our volume at STP for carbon dioxide. Nice. And 6.7 says use the answer in question 6.6 to calculate the rate of reaction in flask A for the first 20 seconds in dm cube per second. So we are required to calculate for the first 20 seconds in dm cube per second. So in order to do that, we know reaction rate is equals to, so this time we'll say the change in volume, because we are using the answer in 6.6. So our reaction rate will be defined as the rate of change of volume of the carbon dioxide. So reaction rate, RR for reaction rate, and then we have that. So remember the reaction rate was, the volume was 0.672, and then obviously initially we assume that there was no carbon dioxide produced, so the initial volume is 0, and then 20 seconds, so our change in time will be 20 minus 0, because initially the time was 0 and then it reached 20 seconds. Then it's just a matter of punching all this in your calculator, and then it will give you the reaction rate will now be 0.03 dm cube per second, right? So for every second that passes, 0.03 dm cube of the carbon dioxide is produced, right? So that's what it means. Then 6.8 says how will the rate of reaction in flask B compare to that in flask A? Choose from greater than, less than, or equal to. So note that our reaction rate here will be determined more specifically by the amount of the carbon dioxide that will be produced. Speed of the reaction will be the same, because in both these reactions we are using the same amount of the nitric acid, so the concentration of the nitric acid is the same, and then we also have 4.5 grams of the same calcium carbonate. So the only thing that is different here is the volume. So in terms of the speed in which these reactions will occur, they will definitely be the same. So remember, when we speak of reaction rate, we are simply speaking of the progression or the speed of the reactions. So the speed of the reactions will be the same. So we are going to say equal to A. Awesome.